Okay, so here we will take a look at another phenomenon. Okay, so this is actually related to the Lorentz force. Okay, actually related to the Lorentz force. So here, the title is force between two parallel currents. Okay, so in the last chapter, okay, so almost the last section in the last chapter, so we learned another form of the Lorentz force. So which is like if it is a current, okay, inside the B field has an angle between them, so there will be FB equals IL cross B. Okay, so that is the another form of the Lorentz force. So here we have two parallel currents. Okay, so the currents can be in the same direction or in opposite direction. So here it says parallel wires carrying current in the same direction attract each other. Okay, and then parallel wire carrying current in opposite directions repel each other. Okay, so they can be attracting or repelling each other. So first, the magnitude of the force on a length L of either wire is FBA or FAB. Okay, so is actually ILB. Okay, so this is actually the Lorentz force. Okay, actually the Lorentz force, and it could be like this one. Okay, this expression. So what does it mean? Okay, so actually here we have a FB equals FBA equals IB LBA. Okay, what does it mean? So it really means that here the subject is the current B. Okay, the current B, the wire B, the wire B is here. So at this position, in this position, so there will be a B field generated by another current, IA. So IA will generate B field in the space. Of course, the wire B will also generate B field. So actually here we suppose both are infinite long wire. Okay, so in that case, BA will be mu 0 I over 2 pi d here. Okay, the distance between them is small d. Okay, so here we mu 0 I over 2 pi d, and should be IA. Okay, should be IA. And then for this one, BB should be mu 0 IB over also 2 pi d. Okay, so only the current are different. So here we actually have this BA. Okay, this BA. BA is the B field generated at the wire B. Okay, so here we can have IB times L times mu 0 IA over 2 pi d. Okay, so you try to collect the terms. You have mu 0, putting it here, and then L you put it here, and then IAIB put it here, and then 2 pi d. Okay, so this is quite symmetry. Okay, this is quite symmetry. So which is like mu 0 L and then IAIB and then 2 pi d. So which means that if you also calculate FAB, which is like IALBB. Okay, so this is the force acting on current A. The force acting on current A, but the B field is generated by the current B. Okay, so here we have actually the same thing, putting it here, and then finally it will be the same forces. Okay, be the same forces. Okay, so this is actually the magnitude. This is actually the magnitude of the force acting between two parallel currents. Okay, so here we can also determine the direction, why they attract each other if they have the same direction and vice versa. So here, let's take a look at this figure. So we have IAIB from bottom left to top right. Okay, so here let us consider the force acting on IB. Okay, acting on IB here. So so first of all, we can actually determine the current, the B field. Okay, the direction of the B field. Okay, so here this is the direction of the current. This is the direction of the current. So you use right hand rule to determine the direction of the B field. Okay, so you use your thumb follow the direction of the current, and then your other four fingers will be like in this direction. So at this point will be like pointing downward. Okay, this is a little bit 3D. So suppose this is pointing downward. So here, based on the right hand rule, okay, based on the right hand rule, we can actually determine the direction of the B field at this point, okay, or at or on the wire B. And also, okay, so IB here, we assume that they are in the same direction, okay? If IB is like that, then this is in opposite direction. So this case is in the same direction. So L will follow the current direction. So L points to top right, okay? So here, we can also determine the direction of the force by right hand rule. Okay, so if you still remember FB or FBA is actually IB, L cross BA. Okay, something like this. Okay, so actually this is L is this direction, and then crossing to the downward. Okay, so the force will be like pointing to the wire A. Okay, so also using the right hand rule, you can determine the direction of the FBA. Okay, and yeah, you can actually practice by yourself. BB is actually pointing downward, and then L also points to this direction. So finally, L cross BB. Let me see, L cross. Oh no. BB is pointing upward. BB should be pointing upward. Okay, should be like this. Okay, so because you have thumb pointing this direction, so your finger at that point is pointing upward. So BB pointing upward, L pointing to the top right. So L cross B will be like L cross B, and then your thumb is pointing to this side. So which means that they are attracting each other. Okay, if it is in opposite direction, which means that if IA is in this direction, and then IB is in this direction. So in that case, L is pointing to this direction, and then BA doesn't change. So in this case, your forefinger point to the lower left, and then crossing downward. So your thumb will be like pointing to that side. Okay, so this will be FBA. Okay, and then this is L for the wire A, and then this is this side. Okay, so your thumb point to this direction, and then your forefinger like pointing downward, like this. This is BB. Okay, so you saw forefinger pointing to that side, and then crossing downward, your thumb will be pointing to that direction. So this is FAB. Okay, so this means that if the two currents are in opposite directions, they will repel each other. If they are in the same direction, they will attract each other. So using this approach to determine the direction of the forces. Okay, so here it says the general procedure for finding the forces on the current y is to find the force. Yeah, is to find the field. Okay, is to find the field due to the second wire, and then using the cross product. Okay, and then using the second form of the Lorentz force. Okay, so and then similarly the two current wire were. Okay, so here it actually naming it by they are parallel and anti-parallel. And parallel means they are parallel and with in the same direction. Okay, and the current are in the same direction. Anti-parallel already defined to be the current are parallel but in opposite direction. Okay, so this is both parallel and current in the same direction. This means that okay, the currents are parallel and in opposite directions. Okay, so this is just a name. Okay, just a name. So yeah, so here this highlight is simplified as a parallel current attract each other and anti-parallel currents repel each other. So these two pages summarize into this simple sentence. Okay, so this part is the Ampere's law. So actually, this is the second law in the Maxwell equation. Okay, second law in the Maxwell equation we learn. Okay, so the last one is the Gauss law in chapter 23. So this is the second one. This one is about the B field, how to calculate the B field. And here as you can see here, this is the Ampere's law. So on the left side, you can also see an integral. And this one, you also have a circle here, means this is a closed something integral. Okay, and then here we have B dot ds. Okay, B dot ds is a line integral. Actually, we have learned the line integral for the electric potential. Okay, so we already faced this one. Okay, so which means that this is a closed line integral or a line integral over a closed loop. Okay, and on the right side you also have something like this, mu 0 I enclosed. So actually this is somehow like the Gauss law. Okay, although that one is a closed surface integral or closed surface integral. This one is a closed line integral. Okay, so here it says the line integral is in this equation is evaluated around the closed loop called an Amperean loop. Okay, so that one called Gaussian surface, this one called Amperean loop. Okay, just a name. Okay, so the current I on the right side is the net current encircled by the loop. Okay, so here let's see how we can tackle this one. Okay, so here in the space we have three currents, I1, I2, and I3. Okay, so you only see a circle with a dot or with a cross. So which means that if I1 and I3 is a circle with a dot, which means that this is an infinite long current, and then pointing out of the page. Okay, pointing out of the page. Okay, I1 and I3. And I2 is a circle with a cross, which means that the current is also infinitely long and then going into the page. Okay, so this is there are three currents in this situation. So here we define a loop, a closed loop. Okay, a closed loop means you start from something and then go through and then going back to the original point. Okay, so this is a closed loop. Okay, so actually this loop can be with any shape. Okay, it can be like a circle, can be like a square, or an arbitrary shape. So as much as it is not a straight line, then we try to cut it into many segments. And let's say this one is ds. Okay, this one is ds. So the ds will be like the tangent direction. Okay, the tangent direction at that point. Okay, so and if this segment is short enough, then we can suppose this ds. Okay, the path there is a straight line. Okay, for a very small small length. And of course, this is a loop. We also should define a direction. Okay, it can be either clockwise or counterclockwise. In this case, this is counterclockwise. Okay, this is counterclockwise. So of course, the tangent line has two possible directions. So this ds will also follow the direction of the loop. So ds will be like pointing to the top right at that point. And of course, in the space, we also should have some B field. Okay, should have some B field. Let's consider it to be like this, pointing to the top right at that point, and it can also be uniform or non-uniform. Okay, so generally can be non-uniform, but if we really need to use this integration form of the Gauss of the impedance law, then probably should be quite uniform. Okay, so the idea is like, okay, we try to separate the loop into many small segments. Each segment can be correspond to the b dot ds. Okay, for this one, and then for every segment, you also have b dot ds. Turns out to be a scalar because it is a dot product. It turns out to be a scalar. So for the whole Amperean loop, you have many scalars from this b dot ds, and then finally you add them together as an integral. So we denote it as this. It is actually the left side. Okay, I mean the left side will be the sum of all these b dot ds adding together. Okay, so on the right side, we have mu zero. Mu zero is a constant, so we already know this is permeability, and then I enclose. Okay, so similar to Gauss law, we need to determine, okay, whether, for the Gauss law, we need to determine whether the charges are enclosed by the Gaussian surface. So if it is inside the Gaussian surface, it counts towards the right side. If it is outside, then we don't count it. Here, this is a loop. Okay, so this is a loop. So here we also count whether the current is inside, is enclosed. Okay, is enclosed by the loop. Okay, so this is pretty straightforward. Okay, so I1 here is of course enclosed by this one. Okay, so you assume you have a line. Okay, you have a line. Okay, so whether you enclose it, or if this is the case, then it is not enclosed. This is enclosed. Okay, so very straightforward. So I1 and I2 is enclosed. Okay, so we will consider this one is enclosed, this one is enclosed, this one is enclosed, this one is not enclosed. So on the right side, you only count towards I1, I2, but you need to be careful about the polarity, whether it is a positive current or a negative current. And of course, you try to use the right-hand rule to determine the direction. So how? Okay, so actually, so you try to use your finger, follow the direction of the loop. Okay, so for this case, this is the counterclockwise. Of course, you use right hand. So don't try to use left hand. Okay, we never use left hand rule. So you use your forefinger, follow the direction. Okay, you use the forefinger, follow the direction. In this case, it's counterclockwise. So your thumb is pointing out of the page, okay? So which means that out of the page is a positive direction. I1 is out of the page, so I1 is positive. I2 is into the page, I2 is negative. And then I3 is not enclosed, so it counts to be a 0. So in this case, you can see plus I1 and then minus I2, okay? So this is the case to determine the direction, okay, or the polarity of the current enclosed by the ambient loop. Okay, so yeah, so actually this is the Ampere's law. So actually we can try to make use of it to determine some simple formula. Yeah, so actually here the B field of a long straight wire with current. Of course, previously we already used Biot-Savart law to determine this one. But not this one. Okay, so actually we will try to use Ampere's law to find the B field for both cases. Okay, so what is these cases? So here we have a wire. Okay, it has a thickness. Okay, it has a radius of capital R. It has a radius of capital R here. Okay, so of course, in this case, we have a current. We have a current. Of course, uniformly distributed on the current. So the first case is we determine the B field outside the straight wire, just like when in chapter 23. Okay, we have a sphere. Okay, with a uniform charge distribution, we determine the E field outside the sphere, and then we also determine the E field inside the sphere. Here we have a wire. Okay, we have a long wire, but with a thickness. Okay, which means we have a radius for the wire, and then we try to determine the B field outside the wire and also inside the wire. Okay. So so the middle blue part is the wire, and then this one is the Ampere loop for the upper case. So this means that this is the Ampere loop, and then this is the current. So so this thing is pretty straightforward. So here when R is greater than or equal to capital R, we have an integration of a B dot ds equals mu 0 I enclosed. Okay, so actually we already know that the B field will be like perpendicular to it. Okay, using the Biot-Savart law, you already know that. So actually, for these cases, okay, with this Ampere loop and then the wire, the axis go through the center of this Ampere loop, Ampere loop. So actually, over the whole loop, the B field are symmetry. Although the B field does not point to the same direction, actually point to the top right at this point, actually point to this side at this point, actually point to this side at this point, actually point to this side. So on and so forth. So actually they are not pointing to the same direction, but the magnitude should be the same. And also, B should always parallel to the ds. Okay, B should always parallel to the ds. Okay, which means that B dot ds becomes B times ds, and then B is uniform. Okay, due to the symmetry. So it turns out to be B times integration of ds. So which means this is the circumference of the circle, which is nothing but 2 pi r. So this kind of argument will appear over and over again. Okay, I won't try to repeat it anymore. So because it is like a standard procedure. circle ambient loop, okay, and then with some symmetry structure, then it always be like that, okay. Integration of b dot ds becomes integration of b times ds, and then b times integration of ds, and then finally turns out to be b times 2 pi r, which is the circumference. Okay, so turns out to be like this. And on the right hand side, b mu 0, and then I enclosed is nothing but I. Okay, the whole I. Okay, so the whole I is enclosed by the ambient loop. Okay, so nothing special on the right side. So finally, you just move 2 pi out to the right side, so b equals mu 0 I over 2 pi out. So which is what we have got using the Biot-Savart law previously for a long straight wire. Although that in that case we assume the wire is very thin without thickness. Here we have a thickness for this wire, but ambient law also tells us that B field is like also like this form B mu 0 I 2 pi r. Okay, r is the distance from the axle. Okay, from the axle with a shortest current to the point you concern. Okay, for the second case, when r is smaller than capital R. Okay, so this will be like here we have a wire. Okay, we have a wire. This is capital R, and then here we assume the ambient loop is somewhere here, okay, with a smaller radius. Okay, so here we also assume that the current is uniform. So in this case, so here I enclose over pi small r square is equal to I over pi capital R square. So which means that only this part is the I enclosed in the middle part. I enclosed in the middle part. Okay. So over the cross section area of the inner circle, so which is pi small r square. And then for the whole current, this is I for the whole wire. So the I over the pi capital R square, which is the total cross section area for the wire. Yeah, so this is the case, and then we can actually have I enclosed is nothing but I times small r square over capital R square. Pi and pi can be cancelled. So similarly, using the Ampere's law, so B dot ds equals mu 0 I enclosed. So for the left-hand side part, this is actually the same cases, B times 2 pi r on the left side, so I don't try to repeat. And then for the right side, mu 0 I enclosed is this one, putting it here. So it will be I times R square over capital R square. So moving this part to the right side, we have B equals mu 0 R and R square can be partly cancelled to be R in the numerator, and then 2 pi R square. Okay, so we have 2 pi, we have R square, so to be 2 pi R square in the denominator. Yeah. Oh, sorry, I forgot the I. Okay, I forgot the I. I should be like here. Okay, here we have a mu 0 I. Okay, so actually we also can derive this one. Okay, the B field inside the wire. So it is somehow like similar to the case when we try to determine the E field for a charged sphere. Okay, if it is outside, then it is just as the same as the normal case. But if it is like inside the wire, inside the sphere, it is like linear increase with the radial distance. So yeah, so this is the case. Okay, so here let's take a look at another sample problem. So here it says the cross-section area, the cross-section of a long conducting cylinder with inner radius A. Okay, so this is the inner radius A, and then outer radius. This is the outer radius, and then the cylinder carries a current out of the page. Okay, so the current is out of the page, like this. And the magnitude of the current density in the cross section is given by J equals C out square. So this is not uniform. Okay, not uniform. We have C equals 3 times 10 to 6 A per meter to the 4th power and R in meters. So what is the B field at a point that is 3 cm? 3 cm is actually right in the middle. Okay, here. Okay, so from the central axis of the cylinder. Okay, so actually here we need to first determine the I enclosed. Okay, because we of course have the ambient loop here. Okay, with the R to be 3 centimeter. But at this moment we can just keep R to be R. Okay, make it a variable, and then finally we can come up with an expression and then plug in the value of R to be 3 centimeter finally. Okay, so first we need to determine the I enclosed, which means that only this part will be count. Okay, the outside part of the current won't count. So in this case, I enclosed will be integration of a J dot dA, okay, or J times dA, okay, because this is the cross-section area, okay, so we can also determine the dA to be like also pointing out of the page, okay, and then I and dA will be like parallel to each other. J dot dA will be like J times dA, so I just skip through these steps. Okay, so here we have a this is J is actually C R square, so we have a C R square here, which is J, and then here, okay, you can already expect we will use the polar coordinate. For the polar coordinate, dA is R d theta. So R d theta for the polar coordinate, okay, as always. Okay, so integration. Okay, so R here should be like integrating from A to small r. Okay, so in that case, for this dummy variable, we try to avoid using r because we already have this r for a proper value, okay, as a upper limit. So here we try to avoid using the same dummy variable. So let's make it like r prime here, so that to avoid r prime as the dummy variable and also r is a fixed value. And then theta, okay, this is the whole 360 degrees, so from 0 to 2 pi, so nothing special here. So here we have a c is a constant, and then integration of the r prime. Altogether we have r prime square and then r prime, so r prime to the 3rd power, and then from a to small r. And then finally we have a d theta. Yeah, they are separable, so d theta is from 0 to 2 pi. So this is nothing but r to the 3rd power. So the antiderivative is r to the 4th power over 4. So it turns out to be r to the 4th power minus a to the 4th power all over 4. And then this one, integrating 1 will be theta. So the derivative from 0 to 2 pi will be 2 pi. Okay, so this is it. And then we can do some simplification. 2 and 4 to be cancelled. So pi over 2 and then times c times r to the 4th power minus a to the 4th power. Okay, so this is the I enclosed. So let's put it here. Okay, I enclosed is pi over 2c and then r to the 4th power minus a to the 4th power. And then here, let me try to draw the graph quickly. This is the Amperean loop. This is A, this is B, this is R, okay? And then we already find the I enclosed. And then this is DA, and then also the I is pointing off the page. Okay, so here we can use the Ampere's law. So integration of b dot ds with a closed integral equals mu 0 I enclosed. On the left side, as always, b times 2 pi r. And then on the right side, mu 0 times pi over 2 c, and then times r to the 4th power minus a to the 4th power. Just put this one here. Okay, so very easy. What we need to find is this b. So we move 2 pi r to the right side. So b will be, yeah, actually we can actually cancel this pi with this pi. These two go down there to be a 4. So here we have a mu naught c over 4. Okay, we have a mu naught c here, and then 4 go to here. So finally, we also have this r and also this term. So let's put it here, and then r to the 4th power minus a to the 4th power. Okay, so here we can plug in all the number. Mu 0 is 4 pi times 10 to negative 7, and then over 4, and then c. Let me see, c is this one. Okay, 3 times 10 to the 6th power. And then r is 3 centimeter, if you still remember, 0.03, I'm sure. 0.03. And then 0.03 to the 4th power, and then minus 0.02 to the 4th power. Then you can use a calculator to find that this is nothing but 20 mu Tesla. Okay, 20 mu Tesla. Mu is 10 to the negative 6. Hopefully you have already remembered that. Okay. So yeah, so what is the B field? It means that we not only need to find the magnitude, but also need to determine the direction. So for the direction, actually you can use the right hand rule. Okay, your thumb follow the direction of the current, which is like pointing out of the page. So your forefinger will be like counterclockwise. So B is counterclockwise. Or actually, DA is also pointing upward. Okay, so DA will be the positive side. Okay, and then finally we also come up with a positive B, which means that it follows the positive direction. Okay, according to the direction of the area vector. Okay, so which means that your thumb points to the out of the page, and then your forefinger is like counterclockwise. Okay, so this is this one. So another part is like this is a solenoid. Okay, so actually this is a solenoid, or sometimes we just call it a coil. So actually this coil, if we have some current, okay, with some current going through this solenoid, it generates B fields. Okay, it generates B field. Okay, so this is quite complicated, okay, but later on we will make some simplification, okay, to make it like just as how simple as a capacitor. Okay, so for capacitor, actually if it is not an infinitely large parallel plate, it will generate some fringe E field. Okay, if it is infinitely large, we will assume the E field between the plates are uniform, and then outside the plate will be like nothing. But if the capacity is have a finite cross-section area, then okay, of course inside the parallel plate part, okay, the E field would still be quite uniform, but outside it, it will generate some fringe E field. Here is a similar case. For this solenoid, it will generate some B field. Okay, mostly we consider this part. Okay, mostly we consider this part. But outside of it, it also have something like fringe B field, and then close to the wire, close to each of the wire, we also have some messy B field. Okay, so let's see, okay, how it is described. So here, the solenoid B field is the vector sum of the field produced by the individual turns. Of course, there are quite a lot of turns for solenoid, or sometimes we call it windings, that make up the solenoid. So for points very close to a turn, the wire behave magnetically almost like a long straight wire, and the line of B field are almost concentric circles, which means it mentioned, for this one, it mentioned this part. Okay, it mentioned this part. So close to a single wire, which needs to be very, very close, because practically the wire won't be like so separate aside from each other. So this concentric circle will only occur when it is close to one of the turn. And actually in the middle point, okay, actually in the middle point, it already like this one is pointing upward, this one is pointing downward. So at the very middle point between the two turns, okay, it will be a perfect zero. So yeah, so it is like a broader line. Okay, so on the left side, it will be a approximately concentric circle around a turn, and then the right to the right side. Okay, so it will be concentric circles for another turn. Okay, so for the second point, the field tends to cancel. The field tends to cancel between adjacent turns. Okay, just as what I mentioned. And then the final point, the points inside the solenoid and reasonably far from the wire, is approximately parallel to the solenoid. Okay, so which means that it actually means this part. Okay, so this is like this. Okay, so if it is farther away from the wire, and is, yeah, so it will be like parallel to the solar axis. Okay, so of course the solar axis is this direction. It's this direction. Okay, so actually, okay, so we can slightly take a look at why the direction will be like that. Okay, so here, this point means this is like out of the page. This is like out of the page. This is into the page. This is into the page. So the current will be like. From that point is like in this direction, and then going back to here, and then going into the page, and then next turn going to that point, and then again going here like this. So it's like a loop, okay, going from here to here, and then to the next one to here, to the next one to here, the next one to here. Okay, something like that. So actually, just for the first point, it tells you that okay, if it is close enough to this one, you can regard it as a long straight y, although it is like a circle. Okay, it is like a circle. But yeah, if it is really close enough, you can consider it's like a straight y. So using your thumb, okay, like follow the direction of the current, which is out of the page here. So your finger will be like counterclockwise, and then here your thumb follows the direction of the current, which is into the page. So your forefinger will be like clockwise. So which is like this. Okay. So which means also for that one. And for the middle part, okay, for the middle part, you just use your forefinger follow the direction of the loop, okay, which is like this, okay. Your finger will be like your thumb will be like pointing to the right side. So this is how we determine the direction of the B field. Okay, so maybe let